uh, symbiosis. Okay, symbiosis and anti-symbiosis. So we have seen in octahedral complexes, we have seen in square planar, and we have seen in like in square planar, we have seen in cis as well as in trans, right? So now going forward, we will see the next type of isomerism, like which is like structural isomerism. Under structural isomerism is the fourth one, which is coordination isomerism. Right. So in coordination isomerism, if you see that these are the complex when the cation and anion, okay, both are complex ions, okay, and they may be exchange of ligands, okay. There only ligand exchange will be there, okay, between these two complex ions. So that we call coordination isomers. Like suppose if we have example, suppose we have chromium CN6, okay, 6 ino, and then one more complex we have along with this cobalt hexaaqua, right? Now these two together are there, these two complex are together, okay. Now in this case, if you see here, what is the coordination isomer for this? So it will be like you will have chromium with water 6 times and cobalt with cyano 6 times, right? So their ligands they are changing. If you see this molecule, see here chromium, here also chromium, but here ligand is cyano, here ligand is water. So this cyano went here and this water came over here. So only ligand is getting exchanged. So that type of isomers we are calling it's a coordination isomer. And overall oxidation number of the complex, like overall oxidation number of this particular thing is constant, right? Whether it is in this form or it is in this form, both the places it will be neutral molecule. Understood, right? Now, likewise, we will have another example also, so it will be easy for you. So, if you have copper NH3 4 times, and then if you have platinum Cl4, right? And you will have copper Cl4, and then you will have platinum NH3 4 times. So, these are also coordination isomerism, okay? This and this are coordination isomerism, right? Don't say that these two are not coordination isomerism, okay? These two are not coordination isomerism, but this one and this one, okay, is coordination isomerism. Here also this one and this one are coordination isomerism, right? Only the ligand is getting changed over here, right? Understood? So this is the fourth type, coordination isomerism. Now, like we have completed the structural part, now we will move towards the theories of coordination chemistry, okay? Theories of coordination chemistry, and whatever the I like we have started these classes in between, okay, like I'm talking about that my YouTube viewer, that we have started, like this will be the third lecture in the YouTube for coordination chemistry. Maybe the previous one, whatever isomer I have completed, that later on I will upload it, okay. So let it be continue like this, okay. So now what you are going to get it, like theories you will get from starting onwards. So let's start with the theories, okay. Now what all theories are present, okay, what all theories are present in coordination chemistry? First let us understand that thing. So theories of coordination chemistry. So what are those theories? To understand the coordination compound's structure, its geometry, its hybridization, its reaction, everything, okay. To know in better way, we should know the theories. What are theories? It is applicable in your coordination chemistry, right? So here, like we have three type of theory which is particularly helping here. So the theory will be like this: first VBT came, then CFT, then MOT, right? VBT is valence bond theory, crystal field theory, and then molecular orbital theory. The most or the more advanced one is molecular orbital theory, right? So here we are going to see everything. It will be a little bit descriptive way. So here it is required much more time to understand this, and the good thing is we have enough time. So we will discuss, okay, very nice mode. So what we have? So we have three theories. First one is valence bond theory, that we call VBT. Then we will have, when valence bond theory is having limitation, we are moving towards the crystal field theory, right? So crystal field theory, that we call CFT. I hope I I hope you have understood this. You have already heard this. Okay, and then C1 is molecular orbital theory. Molecular orbital theory, which we call MOT. Right? Now, one thing you should be knowing this, VBT is entirely based on, I'll take another color. VBT is entirely based on coordinate bond. It says about coordinate bond. Okay, it says that the coordination complex is having coordinate bond kind of thing. As when you move towards CFT, it will say about electrostatic force of attraction. Electrostatic force of attraction, right? Now, as you move towards MOT, here you will find covalent. It will say about covalent bond, right? So the ultimate one is the covalent bond. So different theories saying about different thing, the bonding type in coordination complex. Okay, so the VBT says coordinate bond. Like, why I'm saying this, because sometimes in statement type of question you will get this, like VBT deals with, so coordinate bond, CFT deals with low electrostatic force of attraction. Here the point charge, okay, it will say CFT says point charge, so it is electrostatic force of attraction. Likewise for MOT it is covalent bond. Like for a simpler molecule, we have seen that VBT and MOT. We have not seen CFT over there, right? So in MOT, we have seen for simpler molecule like H2, then we have seen for N2, O2, F2, right? So what we have seen over there, we have seen that covalent nature of bond, right? So likewise here also we will have the MOT, we'll see. So one by one we are going to discuss it. VBT is very small. Let us start with VBT first. So VBT, okay, valence bond theory. Try to understand this. We have metal, like for example, if I take one coordination complex, the very used one is cobalt, NH3 six times, and then Cl3. It means that we have one metal and we have ligand, right? So let me take it in this color. So we have metal, we have ligand. So in this type of bond, it will be like you have metal, you have ligand, and we know that ligand is filled with electron. It's having lone pair or something. Metal should be having empty orbital because it's having d orbital and d orbitals are empty. So what is happening? This lone pair is getting filled in this empty orbital, right? So here what type of bond is forming? So this is forming a coordinate bond, right? What type of bond? This is forming a coordinate bond. It says about VBT because we are discussing VBT, right? So this type of thing is happening. So now, sometimes I saw in a question paper, even in CSR level questions, they are asking that in that complex, like they'll say this is the complex. Suppose this one is the complex, and they'll say that okay, in this complex, which one is Lewis acid? Okay, so like that question you will get it. So always remember that here in this case, who is the acceptor and who is the donor, that you have to see. That is depending on that. Based on that we are saying Lewis acid and base. See here metal is the acceptor, so it will be Lewis acid. It will act as a Lewis acid, right? Here ligand is the donor, so it will be Lewis base. So each and every, okay, small things you should be kept in your mind, because we don't know what type of question it may arise. Because now see, with since so many years exams is conducted, so maybe in their mind something, if they are practicing or something they are teaching in the classroom, or if they face that these are the type of question it can come, like the difficulty level in the student, like it's not a difficulty level, it's like simply understanding level. Okay, if students are not focused towards the basic things, then they will put this type of questions in a question paper, right? So try to understand the things, like here metal is the acceptor, okay, lone pair acceptor, so this will be act as a Lewis acid. Here a ligand is donating, so it will be act as a Lewis base. So we can say that it is a electron pair acceptor, but not always metal will be the acceptor, right? Sometimes ligand, whatever ligand is attached, their empty orbitals, okay, their empty d orbitals, metal will transfer electron, right? So that type we will see what are those. It is like we have LMCT and we will have MLCT, right? LMCT means ligand to metal charge transfer, and MLCT is metal to ligand charge transfer, right? So when that thing will come, we will discuss that also, right? So electron pair acceptor, and this will electron pair, we call it electron pair donor because it is donating and it is accepting, right? So now according to VBT, so we have to see some of the points in VBT because VBT is generally helping only for hybridization, inner orbital or it is outer orbital, and what is the geometry of the molecule. Only for these three. If I put a line, it is only about hybridization. It will say about hybridization of the coordination complex. Okay. Then it will say about hybridization. Then it will say about uh, what also it's structure. Okay, either you say structure or you can say geometry. Okay, it is dealing only this much. Okay, understood? Hybridization, structure, or geometry. VBT is dealing only this much. And then inner orbital and outer orbital, whether your complex is like a more ionic compound or it is organic covalent nature or ionic nature is there, that also it will deal. But more like most of the time we are using this VBT only for structure and hybridization, right? What is the geometry and what is hybridization for that purpose. So now today's class is going to be like couple of classes will be going to be very much interesting for you because first time you are going to see the coordination hybridization in coordination complex. Till now you have seen in inorganic and like inorganic in the sense like uh, we have the group uh, like p block elements and the like only for p block elements we have seen the hybridization, but now first time we are seeing for d block elements also, right? Coordination complex maximum form by the d block elements. So we have to see here. So what are the points? Like you just see according to VBT. Okay, everything will be according to VBT. Okay, here if n minus, okay, according to VBT I'm just writing over here and then I'm writing if n minus 1 d orbital. What does it mean? I'll explain you. N minus 1 d orbital, if it is participating, okay, n minus d orbital, if it is participating for hybridization, okay, then the hybridization is going to be happen to D2sp3. I am talking about for octahedral complex. Understood? And if it is D2sp3 orbit hybridization, I'll talk how it is D2sp3 and how it is sp3d2. That also I'll discuss. If it is D2sp3, then we call it's an inner orbital complex, right? For example, we have taken one example, right? This example only we will take it. For example, you have CO, NH3 6 times, and Cl3. Now, for the hybridization, what is the hybridization for this? For that, what we have to do, first of all, we have to see for like for cobalt, we have to see uh, the electron, how it is like you have to just split with T2G and EG, that is different case. But first you have to just fill up like cobalt. What is the oxidation state over here? Already we have seen it's a +3. Very good. If it is +3, then what is the outermost electronic configuration over here? We know about +2, right? Already I have told you in periodic table for D block element, if you are doing uh, like electronic configuration in +2 oxidation state, it is well and good. So my question is to uh, what will be the outermost electronic configuration of cobalt 2 plus? What I'm asking, I'm not asking cobalt 3 plus. I'm just asking first of cobalt 2 plus. Just you reply this and then we'll go for cobalt 3 plus. That is not a big deal. So kindly reply what is the oxidation, like this is the oxidation number. What is the outermost electronic configuration? I'm just writing 3D. Now, what number I'm going to write over here? after 3D? Can you tell me? We have 3D and we have 4s. So always 4s will be 0, no doubt, because 2 electron already came out. Now what about 3D? Okay, so 3D is 7, right? So 3D 7. Now it is for cobalt 2 plus. Now if I'm asking for cobalt 3 plus, because here we need cobalt 3 plus, here we don't have cobalt 2 plus, right? It is only for general purpose I asked. General. Okay. But for cobalt 3 plus, I'm asking. So it will be 3D6 4s0. And then we know that if we have 4s, then we will have 4p also, that is also 0, and we will have 4d, that is also 0. Now, you just see here 3d means it is n minus 1d, right? If it is 4d, then it will be nd. Are you getting my point? What is the difference between n minus 1d and what is the nd? So if you have, like here, n minus 1 means, excuse me, n minus 1 means, here you just see, here the principal quantum number is 4. So n minus 1 means 3d, right? Because 4 minus 1. Now, if you are not taking the 3d, if 3d is completely filled, now you have to see, you have to take 4d, okay, means nd, you have to take nd for the hybridization or fill up the electron, whatever the from outside it is coming. And if you need to fill up the electron in 4d, then it will be nd orbital, right? Now, what we are dealing over here, we are dealing with n minus 1d. It means, let us draw the box model for cobalt 3 plus. So cobalt 3 plus, if we draw 1, 2, 3, 4, 5. So cobalt 3 plus 1, 2, 3, 4, 5 and 1, 6. Now cobalt at plus 3 oxidation state, as well as if ammonia is there. So if cobalt in plus 3 oxidation state, ammonia will act as a strong field ligand. Don't worry about that. I'll give you what is strong field ligand and what is weak field ligand. Like the number of examples we will practice, with that you will come to know what is a strong field ligand and what is weak field ligand. Fine. So now in this case, if cobalt is in plus 3 oxidation state, then ammonia will act as a strong field ligand. So with that, it will help to pairing it up. Okay, the electron, it will get pairing it up. So this is 3d, this is 4s, and this is 4p. Now we are using n minus 1d. So for that, n minus 1d should be empty, right? So what will happen? Pairing up will take place, right? So it means this will go over here and this will go over here. Now you just see, here it will be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Now 6 electron is over here. Now you have 4s, 3d, 4s, and then you will have 4p. Now, how many ammonia are there? There are 6 ammonia, right? 6 ammonia. As I told you, hybridization is taking place in organic chemistry. Also, you have seen that hybridization will take place like how much demand is there, that much supply you have to do. So now 6 ligand is coming over here. Like 6 ammonia means each ammonia will have one ligand, right? Like one lone pair. So it will act as a ligand. So now 6 ligands are there. So this will go and it will donate its electron pair, right? So where it will donate? See, one pair will be over here, second will be over here, third will be over here, fourth will be over here, fifth will be over here, and sixth will be over here. So 6 ammonia done, right? NH3, 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 and NH3. Now you just see here, this many orbital are taking participate in hybridization. Now you just see, we are using n minus 1d. It means we are using inner d. See, inner d orbital, right? This one, if suppose we are using this d, 1, 2, 3, 4, 5, this is 4d. If we are using this d, that is outer d, right? So if we are using this d, then it will be outer orbital complex. If we are using inner one, that is inner orbital complex, right? So likewise, based on the hybridization, you will find it out whether it is inner orbital complex or outer orbital complex, right? Now this is, we are using inner d. Now just see how many d we have used. 2. So just write d2, 1s, 3p. So hybridization is D2sp3. Now D2sp3, already we know that what is the geometry for D2sp3. See here, that case here, whatever it is coming on the main group chemistry, the hybridization, we were having lone pair and then shape is different, geometry is different. Here it is very much easy. If you are finding the hybridization, directly geometry, you will get it, right? Here we don't have that lone pair kind of conditions, right? Now D2sp3 means steric number is 6. So it will be octahedral, right? It means this is octahedral, but we will say this is a inner orbital complex, right? There also they'll give example like cobalt, NH3. What is that example here? Now they'll ask four options, whether it's a inner orbital complex, outer orbital complex, like that question may be asked. What is the hybridization? What is the geometry? What is the oxidation number? Okay, whether it is a ionic compound or whether it is having ionic character more or it is having more covalent complex, whether it's a low spin complex or high spin complex, everything, right? So just I'm giving, if it is an inner orbital complex, everything is interlinked. If it is an inner orbital complex, okay, then we say that it will behave like covalent complex. Okay, it will behave like covalent complex. If it is behaving like covalent complex, or if it is or if it is an inner orbital complex, then we say that it's a low spin complex. What does it means about low spin complex? Low spin complex means if you have a strong field ligand, means if that ligand is helping to pairing up, like if that ligand is just pairing up the electron, it means that is low spin complex. If those ligands are not having that much power to pairing up the electron in d orbital, then that will be a high spin complex. Like low spin complex and high spin complex, you will understand once we will move towards the crystal field theory, where the splitting will happen. Okay, there this type of splitting will happen where T2G and EG, right? T2G we will have 3 and EG we will have 2. Now see, if we are writing for this cobalt 3 plus, the electron will be like this 1, 2, 3, 4, 5, 6. That's why here, and now these two are empty. So see, this is low. If it is not pairing up, then 1, 2, 3, 4 initial stage, it will be in initially, it will be like this. Initially, it will be 1, 2, 3, 4, 5, and then 6, right? But that if this is the case, then this is high spin. But we know that this is a low spin complex. This is the inner orbital complex. It is using n minus 1d. So this will behave as a covalent complex. So this is low spin, right? Because pairing up is happening. So it will be low spin complex, right? So this is your low spin complex. Understood? So that's why it is. So this thing should be interlinked. Okay, this thing should be in your mind that you have started with this complex. You have to first find out the oxidation number and see, find out, you have the step one will be the finding out the oxidation number. Based on the oxidation number, you have to write the d number of d electron. Then you have to see the ligand, whether it is a strong field ligand or weak field ligand. If it is a strong field ligand, then what you have to do? You have to pair up the electron. If it is a weak field ligand, then no need to pairing up. See, I'm just telling you, if cyno is there, if carbonyl is there, these are a strong field ligand, right? If NH3 is not a strong field ligand, but if cobalt at +3 oxidation state, then NH3 will act as a strong field ligand. If cobalt is +2 oxidation state, then NH3 will act as a weak field ligand. Means their pairing, it won't happen, right? Now, if cyno is there and carbonyl is there, whether it is a +2 oxidation state or +3 oxidation state, it will be always a strong field ligand and pairing up will happen, right? Likewise, I'll give you the list, don't worry about that. Likewise, if you have 3D metal, then this strong field and weak field will work. But if you have like more than like apart from 3D element, like if you have 4D element or 5D element, whatever ligand is present, everything will act as a strong field ligand. Whether it's a ammonia or chloride or fluoride, everything will be act as a strong field ligand and pairing up will happen. Okay, mainly pairing up of the electron will happen. Understood? So if your metal is 4D or 5D element, then pairing up will happen, right? If it is not 4D and 5D, if it is a 3D element, then pairing up will not takes place. That you have to keep in mind. Okay, understood? So now you have understood here, like inner orbital complex behave like covalent complex. It's a low spin complex. Okay, so these are the things you have understood. Now the second point, it says that if if ND orbital is using for hybridization, if ND orbital or maybe the ligand is utilizing to fill up the ND orbitals, then it will be okay. Then this type of orbital is going to be happen. Your like how the flow, and with the same flow I will write, so it will be easy for you. Participating for hybridization is D2sp3, so here it will be sp3 d2. If sp3 d2, then what I have written low spin, so here I'll write inner orbital, so here I will write outer orbital. Okay, outer orbital complex. If it is outer orbital complex, then as I told you, there it is organic, like covalent character or covalent complex, so it will behave as an ionic complex. Okay, ionic complex. Okay, if it is an ionic complex or if it is an outer orbital complex, then it will be high spin complex. Okay, high spin complex means here pairing up will be not taking, pairing up is not taking place, right? Always remember this. Okay, so D2sp3. Okay, D2sp3 is inner orbital complex and sp3d2 is outer orbital complex. We will discuss so many examples, so it will be easy for you. Okay, like one by one example I'll give you. So what is your job? Your job is to find it out first, oxidation number, then you have to write down the outermost electronic configuration, and then you have to find it out the hybridization, right? And then you can easily say whether it's inner orbital complex or it is outer orbital complex, right? Got it? Now, for stability purpose, if thermodynamically stable things you want to see, the inner orbital complex will be more stable than outer orbital complex. Okay, inner orbital complexes are more stable than outer orbital complexes. It means low spin complexes are more stable than high spin complexes. It means covalent complexes are more stable than ionic complexes. So this type of relation you can make it. Okay, so VBT used to determine to find hybridization as well as geometry of the complex. As I told you, we are dealing only with the hybrid. Here in VBT is hybridization and geometry. Okay, so for with the like for doing some of the problems, always remember that when carbonyl will be there, when cyano will be there, this will be strong field ligand. Likewise, whenever NH3 will be there, chloride will be there, fluoride will be there, water will be there, weak field ligand. Understood? This will be weak field ligand. Got it? So strong field ligand and weak field ligand. Understood? Now, if in case of cobalt, only in case of cobalt, if it is +3 oxidation state, then NH3 will act as a strong field ligand. Okay, SFL. And WFL is weak field ligand. So SFL, going forward, I'll write SFL. So strong field ligand, right? In case of cobalt +3. Now, if you will have metal at 4D and 5D series of metal, then all will act. Okay, otherwise I'll not write all will act as a strong field ligand. I'll just write pairing up of electron will happen, right? So with this, your VBT things like this side, like VBT, what we say, the concepts I have completed. Now what we have to do, we have to just see one by one examples and we have to see the hybridization. Okay, so that we will do in the next class. Till now, you just revise it. Okay, keep on revise it. So thank you.